Right. Hi guys. So today we're going to be talking about logarithmic functions and how to sort of go back and forth between exponential and logarithmic form, as well as just writing, graphing, and evaluating logarithmic functions. So let's get started. How many times would you have to double 1 before you get to 8, right? So 1 is your initial value, and doubling is your multiplier. So we sort of talked about this the other day, y equals a times b to the x. If we were to fill this out, what this is really saying is we know our initial value is 1, our multiplier is 2, and we have our final amount, that $8. So what does x have to be in order to get to 8? Well, that's saying 2 to what power gives me 8? Well, I think that's a 3. So remember that x is in the box. We're looking for what's that exponent got to be. And then, once again, same idea here. We have our multiplier is 2. Our original amount was 1. 1 times 2 to what power would give me 512? Well, it's going to be a really big number. It's going to be 9 times. But anyway, that's usually just a good warm-up for us to talk about, but you're not here. This operation of solving for that exponent is sort of like finding the inverse. It's working backwards, right? Usually we're plugging in for x in order to find y. In this case, they're given y and we're looking for x. So a logarithm is the operation to which a specified base is raised to obtain a given value. It's basically saying a logarithm is figuring out what your exponent is, right? You can write an exponential equation as a logarithmic equation and vice versa. So what you're going to see here is if you are looking for that exponent, so we have some base b, sorry. So we have some exponent x that we're looking for. You can write this as a logarithmic expression. Your base b goes here, the total amount a goes here, and then that exponent x is your final answer. So we're going to practice this a little bit by going from your exponential to your logarithmic equation. So this is called log base 3. So your base is 3. And then the total amount that you're looking is 3 to what power gives me 243? Well, that would be 5. Right? So if we're looking at this next question, it says 25 is equal to 5 to what power? Well, in this case, we are looking for the power, so that is going to be that box. Our base is 5 because we're looking for 5 to what power gives me my answer of 25. This is a little bit weird, right? So once again, this is saying 5 to what power gives me 25. Well, 5 squared gives me 25, right? So log base 5 of 25 is 2. So you'd have to fill in that imaginary 2. So here, my base is 10. So I have log base 10. My original answer was 10,000. So 10 to what power gives me 10,000? Well, that would be 4. Something important to take note of is if you ever see something like this without a base, if you just see log of 10,000 equals 4, if there's no base here, you're going to assume the base is equal to 10. It's sort of just a common thing that we use all the time in mathematics, so they drop the 10 just as shorthand. Okay, so this is the more formal way of writing what you just saw here. Log base 10 of 10,000 equals 4. So if you were filling out your logarithmic expression for this. We have our base of our exponential expression, which is 6. In this case, we have our exponent, which is -1, and we're looking for our solution. So 6 to the negative first power, remember we got to move that guy to the basement, so we would get 1 over 6 to the first power. Sorry about the document camera stopping. We're going to restart because apparently that's how things work. And then we're going to continue with, once again, if we were rewriting this, our base is a, so we're going to have log base a. My answer is c, and then my exponent is b. So if you notice, whatever your exponent is always by itself on the right-hand side of the equal sign. The base of your exponential expression is always going to be that bottom piece by the log. And then your final answer is the big number that's written on the side with the log. So let's switch this around a little bit and write our logarithmic form as an exponential equation. So the base of our exponential expression is 9. Our answer for our exponent was 1, so 9 to the first power gives me 9. This next one, our base is 2. Our exponent is 9. 2 to the 9th power is 512, right? So once again, that small number is always your base. The number on the right-hand side of the equation is the exponent, which makes this your answer. So in this case, our base is 8. We don't know our exponent. And we know our answer is 2. Now this is weird, and I'm going to show you how to get this answer, and this is something we haven't really talked about a lot. So in this case, we're going to get 8 to the 1/3 power gives me the cube root of 8. Right? So really what this is saying is what number to the 3rd power gives me 8? Well, that number right here is 2. And that's what you're getting here. This is confusing, and if you're curious, you should look up the concept of a cube root. So once again, that 1/3 is going to be our answer here because we're looking for what number to the 3rd power gives me 8. We're going to work a little bit more with how to do this later on this chapter as well. In this case, we have a base of 4. We know our exponent's -2. So remember, we would have to move 4 to the -2nd, goes to the basement. So I'd have 1 over 4 squared, which gives me 1/16. Right? And then finally, our base b, any number to the 0th power always gives me 1. So once again, our base, our exponent, and then our answer. Right? Okay, so moving on, we're going to talk a little bit more about log base 10 on the back side and then some other little things. A logarithm with base 10 is called a common log. If no base is written for a logarithm, just like we saw before, the base is assumed to be a 10. So this question, if you don't see a base, you're going to assume it's 10. And this question is saying 10 is my base. I don't know what my exponent, but my answer is 0.01. Well, it might help to rewrite this as 1 over 100. And to think about this, 10 to the 2nd power would give me 100, but in order to flip that, I would have to make that negative, right? So 10 squared would give me 100, and in order to flip that, I would have to make this a -2. Same thing here. We have log base 10 of 0.00001. So this is 1/10, 100th, thousandth, 10,000th, 100,000th, right? So I would have 10 to what power gives me 1 over, remember, 10, 100, 1,000, 10,000, 100,000. 10 to what power would give me 100,000? Well, count your zeros, right? 1, 2, 3, 4, 5. But in order to flip that fraction, we had to make it negative. This next question, the way to think about log base 5 of 125, it's saying 5 to what power gives me 125? Well, that would be 3. This next question is saying 25 to what power gives me 0.04? Well, let's write 0.04 as a fraction. That would be 4 over 100, which gives me 1 over 25. So in order to make 25 1 over 25, I would need my exponent to be negative, and I didn't change the number, so I'm just going to use a 1. So hopefully this helps to kind of reiterate the idea of a log. It's usually when you're solving for the exponent. Because logarithms are the inverses of exponents, the inverse of an exponential function, such as 2 to the x power, is the logarithmic function. So it would be log, our base is 2, and then our exponent in this case is x, right? So if we were to graph our original function, so I can use a black pen, so x and then y is equal to 2 to the x power. If we were to plug in -2, -1, 0, 1, 2, 3, we actually did this in your notes from section 7.1, so I'm just going to kind of cruise through this and write down all of these numbers. We already have the work shown in 7.1, so if you're curious, go back and look. Let's graph our exponential function real quick. And then we're going to show you the inverse. If you recall, for inverse functions, those are the ones where you literally reflect over that line. Oops, let's draw a straighter line here. There's 2 ways to do this. You reflect over the line y equals x. Or you can do like I like to do, which is switch your x and your y's around, right? So if I'm doing the inverse function of y equals log base 2, remember the base of my exponential function was 2 and my exponent was x. All we do is switch our x's and our y's. So if my y was 1/4, my x will now be 1/4, and my y is -2. 1/2, 1, 2, 4, and 8. 3, 2, 1, 0, -1, -2. Let's graph these things. My x is 1/4, so we're going to be really close to that y-axis, and then that y value is -2. Half, -1. 1, 0, 2, 1, 4, 2, and then 8, 3. If you look at all of these coordinates, sorry about the sloppiness there, you can see that they are an equal distance from that line of reflection, and you can see how those are inverses of each other, right? So hopefully that helps a little bit. If we were talking about log base 2 of x, right? Let's just draw a little arrow here and show a little work. So if I'm telling you your x is 2, for example, then I would have to write this as log base 2 of 2 is equal to question mark. What this is saying is 2 to what power gives me 2? Well, that value would have to be 1, right? Which is why my y value was 1 up here. So once again, if I'm plugging in some number 2 for x, I have to rewrite this logarithmic expression thinking 2 to what power would give me 2. That power that we come up with is that y value. So hopefully that helps. All right, get started on your homework.